Well, what we do is, pardon me, I'm going to grab a calculator. Let's see if I can get out of here, and I'm going to grab my calculator. And here's what I'm going to do. I'm going to do sine x and print divided by x. All right. Now, we only care about values really, really close to 0. So I'm going to tweak my window, and I'm going to go, let's go from -1 down to 1, And we know that sine never gets bigger than 1 and smaller than -1. So let's go from -2 to 2, just to give ourselves something to look at. -2 to 2, and let's sketch it. Okay. Look at that. Okay, it does appear as though this thing is headed for 1 at 0. There's only one problem, is I don't know, if I were to zoom really far in, I don't know if all hell's going to break loose in here. Something crazy could happen. Remember, we're talking about arbitrary closeness. We're getting very, very, very close to 0, so much so that you can't really tell the difference. And because it's a sine x and an x, and I'm dividing by a 0, all hell may break loose. But watch this. Look at this. Look at that. This is sitting here looking that I've got a table right here. Okay, however, I don't like how this is set. Look at it. It's set at x equals 6, 5, 4, 3, 2, 1, 0. Now, you have the ability to go in and you can set your table. All right, so I'm going to set my table. I'm going to start my table at, I don't know, let's go 0.9. All right, and then now this delta table, I know you guys have all seen this, so bear with me. This delta table here is going to be, let's go 0.01. All right, so if I'm in tenths for my start, then let's go hundredths. If I'm in hundredths, let's go thousandths, etc., etc. Then I simply hit second table and watch what happens. Okay, now, look, I started at 0.9 and I'm going by hundredths, right? So 0.91, 92, 93, and look at my values here. These are important to look at. 0.86, 0.85. Let's see, as I get closer, oh, wait, I'm going, what did I do? Oh, I'm sorry, you guys. That was ridiculous of me. I need to go to 0, don't I? So let's reset that. Well, it's good to see me make a mistake or 6 from time to time. I'm sorry, let's start at what do I want to do? -0.1, sorry. Or 0.1. Let's go 0.1. 0.1, and then we can just go backwards. Go to the table. I apologize for that. It happens. All right, now look at this. I'm going to head back down towards 0. And look at what's happening to my values. As I go down towards 0, see this? I'm going to 0.08, 0.07, 0.06, 0.05. What's happening to my values? They're actually, you can see it over here. This is even a better display. 0.01 at 0. Watch this. All hell breaks loose. Ah, well, we know that. There's no way to algebraically cancel this x in the denominator. I've got this wonderful use of my table to tell me what's going on. Now look, on the other side, do you notice here? 0.9998, 0.9998. They appear to be heading for 1. These happen to be the same values because we know that this function right here is even because both sine x and x are odd. So the negatives cancel and we end up with an even function. All right, look at this. Oh, see, isn't that cool? So these are the same values. By God, it does appear that both values head for 1. All right? So that right there is a numerical way to check for limits. Okay? It's a numerical way to check for limits, which I promise, remember, graphical, algebraic, numeric. And there we have it. All right? Now, as we get further and further into limits, you're going to start relying really heavily on the graphical and the algebraic. The table, this numerical way, is more to get an intuition about what's really going on. Okay? All right, cool. Now, let's talk about one-sided limits. All right? Real quick. So I'm going to talk about one-sided limits. Now, let's talk about why one-sided limits are really here. Well, look at a function like y equals root x. All right? If this is f of x equals root x, okay? And I want to take the limit as x approaches 0 of root x. Well, watch what happens. Check it out. If I do my dental floss technique, right, and I drape, and I do, There's no way for me to approach it from both sides. There's no way for me to carve out intervals, because the function, in other words, open intervals around x equals 0, because the function doesn't live over here. However, it should be relatively obvious that if I can sneak up on x equals 0 from the right-hand side, I'm going to head for 0. So one-sided limits will give us that ability. And let me show you how this is written. Let me change pens. All right, so if I say the limit as x approaches a from the positive side of f of x, this is called a right-handed limit. Right-handed limit. Okay? And what that means is we're simply, in the case of y equals root x or f of x equals root x, we're sneaking up on the right-hand side because it doesn't make sense to talk about the limit from the left-hand side. There is no function to drape my fingers across. So the way in which we would write that is the limit as x approaches 0 from the positive side of f of x. Let's not do f of x. Let's do root x since we know what its name is. Of square root of x is equal to 0. Now, what do you think that, again, let's make this bigger. What do you think that if I take root x again, so this is going to be y equals root x. Remember, I can write it as f of x or y, it doesn't matter. If I talk about the limit as x approaches a from the negative side of f of x, all right, well, that means that's a left-handed limit. Left-handed limit. All right. Well, if I try to take the limit as x approaches 0 from the left-hand side of root x, it doesn't exist. The function doesn't exist over there. So how the heck can the limit exist? Now, watch what happens here. Let's keep this real simple because you're going to get loads of practice on this. So if I have a function, let's say that does this, and then whoop, okay, here, and then here, and then here. Okay, so I know my scale is going to be all jacked, but that's okay. Let's call this 2, and let's call this 4. Okay, and this is going to be f of x. Now, first things first, what is the limit as x approaches 1, let's keep this simple, and 2. The limit as x approaches 1 of f of x. Well, again, take your fingers, put it on the graph. Do they head for the same value? Yes, they do. Guess what? This guy's going to be 2. All right. How about the limit as x approaches 2 of f of x? Well, I'll use red this time. If I put my fingers on the graph, this guy heads for 4. This guy appears to head for 1. Do they head for the same value? If they don't head for the same value, the limit does not exist. However, and oh wait, let me back up. The most common error that students will make is they'll say, wait a sec, the limit is 4 because I know right here that f of 2 equals 4, so that's got to be the limit. No, 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 no. Remember, dental floss. We don't care about what happens at x equals 2, right? As far as we're concerned, f equals 2, f of 2 never exists. We don't care what happens there as far as the limit is concerned. I realize that it's important that we know what the function is doing at x equals 2, but for the purposes of limits, out the window. Don't even care. However, what about if I take the limit as x approaches 2 from, say, the negative side? Well, what does that mean? It means I'm sneaking up on 2 from the left-hand side, which means if I put my finger on the graph, I'm sneaking up on 2 from the left-hand side. So what am I headed for? 4. Let's call this f of x, and this equals 4. Now, what about if I take the limit as x approaches 2 from the positive side? Now, there has been some confusion in the past about what this positive negative side means. This just means the negative side of 2, which means the left-hand side of 2. Like the negative side of the real number line is everything to the left of 0. All right, so this negative has everything to do with this value. Okay, with, in this case, x equals 2. The limit as x approaches 2 from the positive side, check it out. It's already kind of sitting here for us, isn't it? What are we headed for? It appears to be 1. Now, let me show you another really cool ramification of one-sided limits. If I want to say that the limit as x approaches a of f of x actually equals L, this is almost like a theorem. If the limit as x approaches a of f of x actually equals L, what does this imply? What can be said, especially in the context of these new left and right-handed limits, these one-sided limits? Well, think about that. My fingers have to go to the same point, which means the left-handed and the right-handed limits have to be what? They have to be the same. All right? Not only do they have to be the same, but they have to be L. So the limit as x approaches a from the negative side of f of x has to equal the limit as x approaches a from the positive side of f of x. And they both have to equal L. You know what I mean? If I'm claiming that 1 is my limit in this case, well, duh, no it's not. We're both headed for 2. So one-sided limits give us this really, really powerful way to play with the concept of limit. You can take it on from both sides. Okay? All right. Well, that's it for section 2.2. I hope you enjoyed it. We're going to do a ton of these in class, just like always. And I can't wait to see you guys back for section 2.3. Have a really good day.